Hello there, everyone, and welcome to this live session of the Chemistry Clinic brought to you by Boost Revision. I am Dr. Owisi, and a special welcome to anyone joining us from the LAE. Today's session is going to be a Year 12 session looking at alkanes and alkenes. And to start off, we're going to be looking at the properties of alkanes and alkenes, and especially taking a closer look at the bonding found in both homologous series. And then of course, we will be looking at the reactions. So for alkanes, we're going to be looking at combustion reactions, and we're going to be looking at the radical substitution mechanism, and we're going to consider why they aren't as reactive as alkenes. And of course, with the alkenes, we're going to be looking at the various addition reactions that you see alkenes undergo. Now, at various points during the session, I would like to stop and answer any questions you've got. So if you do have any questions, do use the chat box. Towards the end of the session, we will look at some actual practice questions from an exam paper. Again, feel free to drop questions into that chat box, and I will pause to consider any questions you've got. Now, before we start, I'm going to connect my tablet, and then we'll be good to go. So do give me a few seconds while I do that. Okay, perfect. So we're all set. So you should be able to see my start screen, alkanes and alkenes live. And we're going to start by looking at the properties of these homologous series. So the alkanes, of course, you know to have the general formula CnH2n+2. And we can also define them as being saturated hydrocarbons. What do we mean by saturated? Well, it simply means that there are no double bonds to consider at all. So it's just single bonds, carbon-carbon single bonds, carbon-hydrogen single bonds. And all of these bonds are sigma bonds. So that's the first thing we want to pay attention to. So I'll highlight that point for you. So we're looking at sigma bonds in our alkanes. And what are these sigma bonds? Well, sigma bonds are formed from sort of a head-to-head overlap of 1s orbitals, or head-to-head overlap of p orbitals. So I've shown here let's highlight this in a different color. So you can see a 1s orbital in blue highlighted here, and another 1s orbital. And when these two 1s orbitals, each containing one electron, overlap, you end up with a sigma bond. Okay, so we've got a blue sigma bond here from the overlap of two 1s orbitals. Now you can form another sigma bond, but using p orbitals as well. So on the right hand side, I've shown two p orbitals, and you can see these two p orbitals coming together to give you the sigma, the second sigma bond you can see on the right hand side. If I highlight these in yellow, so here is one of our p orbitals and a second p orbital coming together to give you the sigma bond shown there. Okay, so these are the two different ways that you can form sigma bonds, and alkanes contain these sigma bonds. Okay, now in terms of the geometry or the shapes of our alkane molecules, considering the shape centered on the carbon atom in an alkane, this is of course tetrahedral. And so if I use methane as an example, I'm going to draw a molecule of methane here to show the tetrahedral geometry. So you've got CH4 as our methane, and I'm going to draw it in 3D so you can see what I mean by tetrahedral geometry. So that's your methane molecule. And if we consider what shape that methane molecule is, we need to think about our electron pairs and the electron pairs in the valence shell. Okay, so electron pairs are there. We've got 4 bonding pairs. So we can write that to the side, 4 bonding pairs. And because there are no lone pairs, we do need to point that out as well. So 0 lone pairs. And because there are no lone pairs, and we know for a fact that the bonding pairs repel each other equally, we're going to arrange them in such a way to minimize that repulsion. So let's write that down as well. So 4 bonding pairs that repel equally. Okay, and as a result of the 4 bonding pairs repelling equally, we're going to have a tetrahedral geometry. Okay, so therefore it should be tetrahedral. And the bond angles are going to be 109.5 degrees. So if I show you what the bond angle is that we're referring to, so that bond angle there, it's going to be 109.5 degrees. Okay, and that's true for all of the hydrogen, carbon, hydrogen bond angles you'll find in methane or in any alkane for that matter. If you pick any carbon in an alkane and you look at the bond angle it forms to the hydrogens it's bonded to, it's going to be 109.5 degrees. Okay, so the other property that we need to know about is the boiling point. So what the first trend we will spot with the alkanes is that the boiling points increase with the relative molecular mass of the alkane. So again, we can make a note of that, and if we write that down, so boiling point increase with the MR. Okay, so why should the boiling points increase with the MR? Well, in order to answer this, you need to think about what sorts of forces we're trying to overcome when we try to boil an alkane. So we need to think about intermolecular forces and specifically induced dipole-dipole forces or London forces. Okay, so the larger the MR, so the larger the MR, the greater these forces will be. So, and why? Because there are more electrons. The larger the MR, the more electron density, and therefore the stronger or larger the induced dipole-dipole attractions. Okay, so I've got more than one dash there, but you can forgive me for that. Okay, so if I use my rubber, let's get rid of that. There we go, and write that properly. Okay, so induced dipole-dipole. So if you have alkanes of increasing size, then you're going to have more electrons in those larger alkanes, so the alkanes with a larger MR. And as a result, you're going to get stronger induced dipole-dipole attractions, stronger London forces. Okay, so boiling points are determined by these intermolecular forces, these London forces. Now, the other thing to note is sometimes when you have 2 isomers of the same alkane, of course, if you have isomers of the same alkane, they've got the same molecular formula, but different structures. But as a result of having different structures, let's say you have a branch chain versus a straight chain alkane, the ability to pack these molecules together differs or changes. Okay, so if you have a straight chain alkane, you can pack them more closely, and that means that your London forces are stronger. Okay, and if you have a branch chain isomer, you can't pack it as closely, and you'll have weaker London forces. So that's another point we should make. So let's do that in perhaps a different color. Okay, so straight chain isomers also have stronger dipole-dipole compared to branch chain. Okay, so that's what we want to talk about as far as the properties of the alkanes are concerned. So we've looked at the bonding, we've talked about the fact that you've only got sigma bonds, we've talked about the bond angle and counting bonding pairs and lone pairs. We've looked at the trend in boiling points, so increasing MR and therefore increasing electron density and therefore stronger London forces or induced dipole-dipole interactions. The next thing we want to consider as far as the alkanes are concerned is their reactions. Okay, so looking at reactions, the first thing to note about the alkanes is that they are relatively unreactive. And we need to consider why this is. Okay, so for the alkanes, you've got strong carbon-carbon and carbon-hydrogen bonds. And in other words, you've got bonds that have a high bond enthalpy or relatively high bond enthalpy. A lot of energy would be needed to break these bonds. And as a result, they are sort of unreactive. It's difficult to break those bonds. And so the first thing you want to say in answer to the question, if you are comparing the reactivity of alkanes or the lack of reactivity of alkanes versus alkenes, which are more reactive, which we'll come to very shortly, you want to talk about the high bond enthalpy. So I'll highlight that there. So we've got high bond enthalpies of the CC and CH bonds in alkanes. And the other thing to note about the alkanes is that none of the bonds are particularly polar. So there's very little difference in electronegativity between the carbon and the hydrogen atom. And so you don't have polar bonds in your alkanes, which means that they're not susceptible to attack by nucleophiles. Remember, so nucleophiles want to attack something with a delta plus on it, but if there are no delta pluses or delta minuses, because there are no polar bonds, then you're not going to get nucleophilic attack. Okay, so the bonds are non-polar. So these bonds are very non-polar, which is what I state here. So they can't be attacked by nucleophiles, which leaves very little in the way of reaction options. So combustion, which is burning in oxygen, whether in excess oxygen or a limited supply of oxygen, so complete combustion and incomplete combustion. And then we'll look at radical substitution, which is another reaction pathway available to the alkanes. But let's write two quick balanced equations for your complete and incomplete combustion, something you've been doing since GCSE, and so you should be able to whiz through this without really thinking, and we'll look at the more challenging radical substitution reactions of the alkane. So let's complete our set of notes here. So we've got methane reacting with oxygen, and if we're saying that you've got an excess amount of oxygen, so complete combustion, you're going to be forming carbon dioxide as one of the products, and you're also going to be forming water. Okay, so if we then look at the numbers of moles of atoms of each element, we've got 4 moles of hydrogen atoms on the left-hand side of that equation. So you've got 4 hydrogen atoms, and so we want the same number on the right-hand side. So 2 moles of water should be formed to give you the correct number of moles of hydrogen atoms. And that now leaves us with 4 moles of oxygen atoms on the right-hand side, and so we need the same on the left-hand side, so 2 moles of oxygen would be required. Okay, so this is the complete combustion of methane, where you have an excess of oxygen. Okay, now if the supply of oxygen is limited, you will end up with incomplete combustion, which leads to the formation of a toxic gas. And again, from your GCSE days, you may be able to tell me that this toxic gas is carbon monoxide, so CO, and again, water will be formed. And then you have to go through the same process of checking the numbers of atoms on both sides. So again, we've got 1 mole of CH4, so 1 mole of carbon, so you should expect to form 1 mole of carbon monoxide, so 1 mole of carbon atoms on the right-hand side. And then if we consider that you've got H2O and 2 moles of hydrogen on the right-hand side, we have 4 moles of hydrogen on the left-hand side. That means that we will need 2 more on the right, and so you can put a 2 in front of your water, and that gives you the right number of hydrogens. Now, counting the number of oxygens, we now have 3 moles of oxygen atoms on the right-hand side, and so on the left-hand side where we've got 2, a quick way to do this is to multiply that 2 by 1.5. Okay, so that might look a bit odd for some of you, but having got 1.5, you can then multiply the whole thing, the whole equation through by 2 to get a whole number. Or you can leave it as 1.5. It just means you've got 1.5 moles. Remember that the mole is Avogadro's constant. It's a very large number, 6 times 10 to the 23 or thereabouts. So you can have multiples of it. So you're saying you've got 1.5 times 6 times 10 to the power 23. Okay, so that's our balanced equation for incomplete combustion. There is something interesting to say about carbon monoxide. Of course, it is a toxic gas, if we highlight that. So that's carbon monoxide, highlighted for you in blue. And it is a toxic gas, so we can sort of make a note of that. And why is it toxic? Well, it binds to hemoglobin in red blood cells much more strongly than oxygen does, and that then limits the ability of your blood to transport oxygen around the body to various cells, various tissues. Okay, so toxic gas binds to hemoglobin. And as a result, it sort of limits oxygen transport. Around the body. Okay, good. So that is the simple sort of the simpler of the two reactions we need to know about when it comes to alkanes. The second reaction is, of course, the radical substitution involving alkanes, where you end up forming halogenic alkanes. And I'll pick so the simplest alkane, methane, as our example to look at this reaction. So you've got the overall equation written for you. When methane reacts with chlorine in the presence of UV light, you end up forming chloromethane, and you end up forming hydrogen chloride gas as well. Now, it doesn't matter what alkane you choose, you will end up forming that chloroalkane and hydrogen chloride gas. There is a bit more to it than I'm making out, and I will talk about this very shortly. But let's assume that we're only replacing one of the hydrogens of our alkane with a chlorine atom for now. So we need UV for this reaction to happen at all. And why do we need UV? Well, it turns out that UV light is the correct amount of energy, the correct wavelength or frequency to break your chlorine-chlorine bond homolytically. In other words, when the chlorine-chlorine bond breaks, each chlorine atom takes one of the electrons in the covalent bond to itself. Okay, so this first step where the chlorine-chlorine bond breaks is known as the initiation step. So this is highlighted in yellow here. So Cl2 absorbs UV light, and you get two chlorine radicals, and the chlorine radicals are highlighted in yellow here. And you show your radical species by having a dot on that radical species, indicating that it has been produced by homolytic fission. You're breaking a covalent bond, and each atom either side of the bond gets one of those two electrons. Okay, so that's your initiation step. That needs to happen before our the rest of our radical mechanism can follow, and that is why you need the UV present. So once you form the chlorine radical, these radicals are very reactive species. They will then react with your methane. Okay, so in reacting with the methane, the chlorine radical will remove one of the hydrogens of your methane to form HCl. Okay, so here's your propagation step, and we'll highlight this in pink. So in your propagation step, you've got your methane reacting with your radical species, and as a result, you end up forming HCl and another radical species. Okay, so the thing to note about the propagation step is that you're taking one radical species, reacting it with a non-radical species, and then you form the same radical species and a non-radical species. So if we highlight this here, so you've got the radical species being reacted with a non-radical species, if we highlight that in pink, and you end up forming another radical species, this time your methyl radical, and you end up forming your non-radical species. Okay, so there are two reactions in your propagation step. Having formed the methyl radical, it will go on to react with a non-radical species, this time round chlorine, a chlorine molecule. Okay, and that chlorine molecule shown there, reacting with your methyl radical, will end up giving you your first mole of chloromethane. Okay, so chloromethane is the product we're after. So we highlight that there in pink, and you can see that your chlorine radical is produced as the second product in your second propagation step. So with all propagation steps, there'll be two reactions. Each of those two reactions involves a radical, and a non-radical species. So a chlorine radical and your alkane, and then in the second step, your alkyl radical and a chlorine molecule. Okay, and then this sort of radical mechanism comes to an end when two radical species come together and terminate. Okay, so there are a number of termination steps possible, and each involves two radical species coming together. So if you look at the third step and the various reactions involved, and this time round, if I highlight them all in yellow, you've got radical species coming together, so methyl and chlorine radical species to give you your chloromethane, another molecule of chloromethane. You've also got two alkyl radicals, so two methyl radicals that can come together to give you another alkane product, so this time round ethane. And you can also have two chlorine radicals, of course, coming together to reform chlorine, which, if there is UV light still present, can be broken down again to give you your chlorine radicals back. Okay, so as far as alkanes go, this is the second and sort of perhaps more challenging reaction to be able to recall and to be able to discuss the mechanism for. Okay, so unlike other mechanisms you'll see in organic chemistry, you're not required to show curly arrows here. So sometimes you'll come across sort of half-headed sort of curly arrows for this mechanism, but you don't need to worry about using those half sort of curly arrows in this instance. Okay, so that's radical substitution and that's combustion for alkanes. Now at this point, I'm just very quickly going to check, see if there are any questions for me. There aren't at present, but if there are, please do use the chat box and I will pause to consider and answer those questions for you. Now, we're going to move on to alkenes, and we're going to be contrasting alkenes and the bonding and reactions with what we've seen with alkanes. Okay, so if we move on to alkenes again, you've got the general formula here, so CnH2n in contrast to the alkanes, which we had as CnH2n plus 2. And that means that the alkenes are unsaturated. You don't have as many hydrogen atoms as could bond to the carbon atoms that you've got. In other words, or in simpler terms, you have a double bond. Okay, so we've got a carbon-carbon double bond present in our alkene. So they are unsaturated. And if we highlight that fact, so unsaturated hydrocarbons, and they have a double bond. Okay, so carbon-carbon double bond. Now, interestingly, the two bonds that make up our carbon-carbon double bond are different. Okay, one you're familiar with already because we've mentioned sigma bonds when we talked about alkanes. So you do have your sigma bonds, if I highlight that in pink, and we have another kind of bond, the pi bond. Okay, so each double bond in an alkene has a sigma and a pi bond making up that double bond. Okay, so what does this actually look like? I've drawn a three-dimensional sort of representation of ethene, so that's C2H4, and I've labeled all of the sigma bonds present and the one pi bond that you've got. Okay, so if you look closely at each of the sigma bonds, which I've highlighted here in yellow, I've written a sigma sort of sign in blue, lowercase sigma, and these are all the sigma bonds present in our ethene molecule. Now, above and below the plane of the carbon and the two carbons and the four hydrogens, if you imagine them being in a flat plane like this, a bit like I'm showing with the palm of my hand, above and below that plane, you've got your pi bond. The pi bond is split into two halves of two lobes. Okay, so if I highlight that for you, you've got your pi bond, and that is highlighted in blue here, and that is above and below the plane of your atoms, and it's above and below, perpendicular to the plane of your atom. And how that is formed is quite different to how your sigma bonds are formed. So sigma bonds are formed when you've got head-on overlap of two s orbitals, or head-on overlap of two p orbitals. This time round, we need sideways overlap of our p orbitals to form a pi bond. Okay, so sideways overlap is crucial. Okay, and as a result of that sideways overlap, you're going to get the pi bond shown on that page. Now, a crucial difference between the sigma and the pi bonds is the bond strength. Okay, so the pi bond is a lot weaker than the sigma bond, and that's because you don't get as good an overlap when you overlap the two p orbitals sideways. Okay, so something to note. So pi bonds are weaker. Okay, so weaker than sigma bonds. Okay, the other thing to consider is the geometry or the shape about your carbon atoms in your alkene, so the double bonded carbon atoms. Now, again, going through the same process we did for working out the geometry of the alkanes, we need to consider the number of bonding pairs and the number of lone pairs, if there are any. Okay, so in this instance, we will have three regions of electron density. So looking at the alkene, let's again use ethene as our example. Okay, so we've got essentially three regions of electron density. The double bond counts as just one region of electron density for the purposes of our electron pair repulsion theory. Okay, so we've got three bonding pairs is what we should say. So three bonding pairs. And there are zero lone pairs. Okay, and if the bonding pairs are going to repel equally, the best way to arrange them would be to give a trigonal planar arrangement and 120-degree bond angle between the carbon and hydrogens. Okay, so bonding pairs repel equally, and as a result, we've got a trigonal planar shape. Okay, so the bond angles would be, say, 120, and it'd be the same here, and it'd be the same there. Okay, so 120 degrees all around. Okay, so that's all we need to know as far as the geometry about your carbon atoms that are double bonded in your alkene. Okay, the other thing we need to consider before we look at reactions is the presence of, or the possibility of, stereoisomerism in alkenes. Now we've had a live session and a video that looks at stereoisomerism and indeed isomerism in a great amount of detail, and I'd ask that you watch that video to refresh your knowledge of isomerism in general. But I'll very quickly point out the existence of a kind of stereoisomerism, or a type of stereoisomerism, so EZ stereoisomerism to be specific. So we're looking at EZ, and we're looking at how to assign E or Z stereochemistry to an alkene that is exhibiting EZ stereochemistry. So I've got two examples shown here, and in both examples you've got a double bond, and for each of the carbon atoms, so if I highlight each of the carbon atoms in the double bond, so we're looking at that carbon and that one, and we're also looking at these two carbons here. Each of those carbons we've highlighted has got two different groups bonded to it. That is incredibly important if you're going to get EZ stereoisomerism. Okay, so that's the first condition. And the second condition, of course, relies on the fact that the carbon-carbon double bond can't rotate, unlike in the alkanes. Okay, so the presence of that pi bond prevents rotation or restricts rotation. Okay, so We could annotate that and remind ourselves of that fact. So no rotation. And we've got two different groups. Okay, so if you've got these two conditions satisfied, then you're going to get EZ stereochemistry. Now, how do we assign E or Z? And remember, E is for antagon, which means on opposite sides, and Z is together on the same side. So we should be writing the German. It'd make a bit more sense to write zusammen and then say what it means. So let's write that down. Okay, and that simply means together on the same side. Okay, so let's look at the two groups we've got bonded to those carbon atoms I've highlighted. You've got a methyl group here, which I will highlight in a different color. So we've got a methyl group, and we've got an ethyl group here. Okay, now in assigning priority for the two groups you've got attached to a carbon atom, you need to consider the atomic numbers of atoms as you move away from the double bond. A lot of students get this mixed up and use mass numbers or look at the size of the group and then assign priority on that basis, which can and often leads to incorrect stereochemistry being assigned. So the rule, again, I'll say it, but if you want to see the full set of rules, I've got it in my previous video on stereochemistry. But you want to start by moving along from the carbon atom, one atom away. So we're now considering, I'm going to use red to highlight it, we're now considering these two carbon atoms that I have shown with red stars. Now, when you've moved one away from the double bond, you want to look at which has got the higher atomic number. Now, of course, we've got two carbon atoms, and so you don't have a point of difference. They both have the same atomic number of 6. And so what we need to do is to move one atom away again until we have a point of difference. And so we can do that. If we move one atom away, and I will use blue to draw in some hydrogens. So we've got hydrogen and a hydrogen here, and we've got 3 hydrogens here. Okay, so if we move one atom away, we will have a carbon on one branch, but hydrogens on the other branch. So if we look at our carbon atom there versus this hydrogen here, immediately you can see that you've got a point of difference, and you've got a carbon atom that has an atomic number of 6 versus a hydrogen with an atomic number of 1. Okay, so immediately you've got the higher priority group being this group up here. So if we label that as such, so higher priority, okay, and this group would be the lower priority. Okay, so on that basis, we can very quickly say the same on the other side. This would be higher priority, and that would be lower. Okay, and if the two higher priority groups are on the same side of the double bond, which is the case in this case, you've got the Z isomer. Okay, so for this compound here, we do have the Z stereoisomer, which we can highlight. Okay, so we've got the Z isomer, and that automatically makes the its counterpart on the right-hand side the E stereoisomer. Okay, so this would be the E because the two priority groups. So if we highlight that, okay, so the two priority groups, the ethyl groups, are on opposite sides of that double bond. Okay, so that was a bit of a quick refresher on using the Kahn-Ingold Prelog rules, the CIP rules, to assign EZ stereochemistry. As I said, I have a video, a much more detailed video entirely on stereochemistry, and a large part of that is looking at examples of EZ stereochemistry. So do look up that live session, and by all means do ask questions if you're unsure about anything you find in that video. Okay, so at this stage, before we look at reactions of the alkenes, I just wanted to have a quick look to see if we've got any questions. There aren't at the minute, none that I can see. So we will carry on with our work and move on to reactions of the alkenes. Okay, so the alkenes are much more reactive than the alkanes. It's something, if there's one thing you're going to leave this session with, it's that could be this this point here. So alkenes are much more reactive, and as we said, that's because of the lower bond enthalpy, the weaker pi bond. Okay, so low bond enthalpy of your pi bond is what explains this. Okay, so the alkenes react by breaking the pi bond. So your double bond has got 2 bonds, we said. The sigma bond's very strong, the pi bond isn't as strong, and it's the pi bond that breaks, and when it does so, you can get electrophiles being added across that double bond. Okay, so electrophilic addition to alkenes. So the first thing to point out, or perhaps to say, is what an electrophile is. An electrophile is an electron pair acceptor. Okay, so it will accept a pair of electrons from the pi bond of your double bond. Electron pair acceptor. Equals electrophile, and once you've got that, it becomes a bit more, so the mechanism becomes a lot clearer. Okay, so let's look at how to add electrophiles across the double bond of an alkene. Now, there are a large number of candidates for addition across the double bond on the OCR A-level course, but thankfully for students, they all proceed via the same mechanism. There's very little difference as far as the mechanism goes for the different electrophiles you need to know. Again, I have done a video on the electrophilic addition mechanism along with other mechanisms, and I've done a live session on this. So a lot more detail there and a lot more examples, some difficult examples as well. So once we've done this, if you want to get some more info on electrophilic addition, I'd suggest you look up that live session on the electrophilic addition mechanism. So how do we add hydrogen bromide across the double bond, across this alkene double bond? Well, your hydrogen bromide, if I draw it again, is a polar molecule. So you've got a delta plus on the hydrogen and a delta minus on the bromine. And so you should have your electrons of the pi bond in that double bond being attracted to that hydrogen atom. Okay, so the first curly arrow you're going to draw will be from the middle of your double bond, so from the pi bond to the hydrogen of your HBr. And as a result of that incoming pair of electrons going to that hydrogen atom, the electrons in the HBr bond will be repelled away from the hydrogen, and this causes the HBr bond to break. So that's that second curly arrow there. Let's just double check that it's all on screen. Yep, it's good. Okay, so those are the first 2 curly arrows you're going to draw. And then as a result of that, you want to show the intermediate formed. Okay, so we've added our hydrogen to one carbon, and the other carbon is of course missing, is electron deficient, is missing an electron, so we'll have a plus charge on it. But we've also formed a bromide ion as a result. Okay, so we broke the HBr bond, and that formed a bromide ion. And so we now have an intermediate, a carbocation intermediate, which can be attacked by our bromide ion. So the lone pair on the bromide ion is going to attack our carbon with a plus charge on it. And when it does that, you end up forming a carbon-bromine bond. Okay, so there we go to our product. And you've got, as a result, the addition of hydrogen and bromine across that double bond. Okay, so think of the curly arrow, yes, as a movement of a pair of electrons, but it's also telling you how new bonds are formed and how bonds are broken. So the first bond formed is between the carbon and the hydrogen, so the curly arrow from the middle of that double bond to the hydrogen, and then your HBr bond breaks, and so you've got a curly arrow from the middle of that bond going onto the bromine. Now note that with our carbocation intermediate, you've got a plus charge on it, and we also have a bromide with a minus charge, and you can see that in that intermediate step, the charges cancel out, just as the reactants on the left-hand side of that arrow have no charge at all. So we're always conserving charge, which is another important thing to note if you're checking the accuracy of your mechanism. Okay, so that is the addition to ethene, which is, of course, a symmetrical alkene. If you're adding an electrophile across an unsymmetrical alkene, things can be a little bit more complicated. So I'm going to look at this example of addition to propene. Again, I do go into this in a lot more detail in my previous live on the addition mechanism, so do check that out. But let's have a look at this example. So again, we've got HBr, and we've got a delta plus on the hydrogen and a delta minus on the bromine again. Now, first curly arrow is exactly as we drew before. So pi bond, electrons in the pi bond attack the hydrogen with the delta plus, and as a result, the HBr bond breaks. Now, we're going to form another carbocation intermediate. Problem here is, of course, that there's the possibility of forming two different carbocations. So the hydrogen could add to carbon number 1, okay, or it could add to carbon number 2. So we've got the possibility of, we use a highlight to show this, we've got the possibility of the hydrogen adding to there or adding to there. And depending on where it adds to, you're going to get two different carbocations. So let's draw the two different carbocations formed. So you can have this carbocation here, okay, which is a secondary carbocation, or you could have this carbocation here, which is a primary carbocation. So if we label those, we've got a secondary carbocation, and we've got a primary carbocation here. Okay, now one of these two carbocations is more stable than the other. It's the secondary carbocation, and again, we talk about the positive inductive effect in my video on this mechanism. So the positive inductive effect, well, simply put, alkyl groups tend to push electrons away from themselves towards a positively charged atom. So you've got this positive inductive effect towards the carbon with a plus charge on it, and in doing so, the ends of that secondary carbocation become a little bit more positive, and the original positive charge gets smaller because it's receiving electron density. And the result of this is to spread the plus charge over the entire carbocation. That makes it more stable. With your primary carbocation, they can only do this from one alkyl group, the ethyl group, pushing electron density towards that plus charge. Okay, so the secondary carbocation is more stable due to greater positive inductive effect. Okay, so if we highlight all of that, let's put that in a yellow box. Okay, so secondary carbocations are more stable because they have a greater positive inductive effect. And so you're going to get the product from the secondary carbocation being formed as the major product. Okay, so leading to the major product. So if we label our two products here, major and minor products, okay, our secondary carbocation forms the major product. Okay, how does it do that? Your Br minus ion is going to attack that carbon with a plus charge. Okay, and the minor product is going to be formed similarly if the Br minus attacks the plus charge of your primary carbocation. Okay, so that is, in a nutshell, the electrophilic addition of HBr to your unsymmetrical or asymmetrical alkene. There are a number of electrophiles that I mentioned can add across the double bond. So, for example, the hydrogen molecule can be added across an alkene, typically catalyzed by nickel. Okay, so other electrophiles we could make a list of. Let's do that before we look at some practice exam questions. So other electrophiles. Electrophiles are going to be shortened to E+. Okay, and so could be, you could have H2 and nickel, where you end up in a catalytic hydrogenation of your alkene double bond. You could also have steam, H2O, and phosphoric acid, or concentrated sulfuric acid. So that would be hydrating your alkene, and that would give you an alcohol. You could also have, let's see, we could also have halogens. So you could also have Br2 being added across your alkene double bond. That gives you a dibromo compound, or it could be a dichloro if you're using chlorine. Okay. The important thing is that the mechanism is the same. Attack by the pi bond of your double bond to one of the atoms of your electrophile. So the atom that is has a delta plus charge on it, and then your breaking of your covalent bond in your electrophile, and then your formation of your carbocation intermediates, and then your halide or your negatively charged intermediate attacking the carbocation. Okay, so that's your electrophilic addition mechanism shown on screen. Again, I'm just very quickly going to check that there aren't any questions. If there aren't, I will move on. It doesn't look like there are. So let's have a look at some practice questions. I've taken these questions from your AS 2016 paper. These are some questions on some various aspects of alkanes and alkenes. So looking at bonding, counting numbers of sigma and pi bonds, looking at some of the reactions we've just discussed as well. So before we even do that, I did forget there's one other, there is one point about alkenes that we haven't discussed. Again, I have an entire video on polymerization, both addition and condensation polymerization, which you do in year 13, certainly on addition polymers. And so I will very quickly sort of look at one example of addition polymerization involving alkenes, which is ethene. Okay, so if you take an alkene, it is a very useful monomeric molecule. In other words, you can join up thousands of these alkene molecules together to form a much larger polymer. Okay, so in this case, our monomer is ethene, which you can see here. And the N that we've got here refers to a very large number, so typically sort of 10 to the 3, so 10 to the 4 of our monomeric alkene, in this case ethene. And over on the right-hand side, we can see the structure of the polymer formed, and this, of course, is polyethene. Okay, and note that in naming the polymer, you have poly before your alkene monomer. Okay, so even though the product formed is effectively a very, very large alkane, in terms of naming it, it's polyethene, polyalkene rather than the polyalkane. Okay, so we've got polyethene shown there. And then there is a second, I did say one example, in fact I do have sort of three examples. There is a second example shown here of propene, which goes on, of course, to form polypropene. And note how the extension bonds are drawn when you draw the structure of polypropene. Let's label polypropene first of all. Okay, so the extension bonds, which I will highlight in yellow, okay, these are drawn from the two carbons that have the double bond between them. So whenever you've got an alkene monomer, draw it in such a way that you can have any side groups sort of coming perpendicular to the backbone of your polymer form, so that it becomes easier to see where the extension bonds are. So this, I highlight my methyl group in pink here. There's that same methyl group in pink, so dangling sort of perpendicular to the backbone of our polymer. And if you draw it that way, it becomes easier to see where the extension bond should be drawn when you draw the structure of your polymer. Okay, now sometimes you are required to work out the repeat unit from a section of the polymer, and then from that work out the monomer it's come from. Now the repeat unit is simply the section of the polymer which, when repeated, will give you the overall polymer. And so if we highlight the repeat unit in this section of the polymer here, that is what is repeating throughout this polymer. You've got what is chloroethene. Okay, so if we draw the section or repeat unit, let's draw it out here. You've got Cl and hydrogen. And so there's your repeat unit. And if we work backwards to the monomer, hopefully you should all be able to work out that you've got chloroethene. Again, chloroethene is also known as vinyl chloride, and of course we've got polyvinyl chloride here. Okay, so this is a section of polychloroethene or polyvinyl chloride. Okay, so that's all I'm going to say on alkenes and addition polymerization. As I said, I've got a quite extensive video on polymerization and addition polymers. But what I want us to look at now to conclude our session are a few questions from the AS Paper 1 2016 paper. Quite a few questions. Some of them are MCQs, so we shan't spend we wouldn't be spending a huge amount of time trying to work out the answers, hopefully. So questions 15, 16, 17, 19, 26A and 26C part 1. And incidentally, I have shared the PDFs, or rather the PDF of the question paper with you in the chat box. I've also got the data booklet if you want to follow our sort of this little exercise. Okay, so the first question we want to look at is question 15, which looks at sort of non-polar molecules. So in looking at the bonding in alkanes and alkenes, we looked at the fact that they're non-polar, especially the alkanes, and so not susceptible to electrophilic attack. If we draw each of the examples shown here, so A, B, C, and D, that's how you would approach solving this. So we've got 1,2-dichlorobutene. So we've got butene, I should say, and it's the E isomer. So we've been looking at isomerism, and so we've got butene shown here, and we're told it's 1,2-dichloro. So we've got Cl there, we've got Cl here. Okay, so E12. Sorry, what I've drawn there is actually B. Okay, so this is B. I've drawn 2, 3. So let's draw A, which is 1, 2. So again, we've got Cl here, and a Cl here, so that is A. And then if we draw the Z23 dichloro, we're going to have a Cl here and a Cl here, so that would be C. And if we draw D, which is 1,4-dichlorobutyrene, so 1,4-dichloro would be that. Okay, right, so now that we've got all four structures drawn, we want to, of course, in each of those structures, we've got polar bonds. Each of the carbon-chlorine bonds is polar, with the delta minus on the chlorine atom and a delta plus on the carbon. But if there are polar bonds which are cancelling each other out, in other words, you've got a symmetrical molecule, then overall that molecule is going to be non-polar. Okay, so with A, you can have a dipole moment in that direction. Okay, so with the polar, in B, you've got a dipole moment there, cancelled out by a dipole moment there, and in our CLC, in our C, we've got a dipole moment here, and we've got a dipole moment here. Okay, so again, remember that the carbon-carbon double bond has no rotation about it, so those chlorines in C are fixed, as well as the chlorines in B being fixed. Okay, so there is an overall dipole moment this way. There's no dipole moment in B. So B is not polar overall. In A, even though one of the chlorines is fixed, the other isn't. There is bond rotation here, so you can potentially have the two chlorines contributing to a net dipole moment, and the same is true for D, and so the answer is B, which is the only one where the chlorines are fixed and can't move. Okay, so correct answer is B. We use black, and there we go. Okay, and then if we look at question 16, we're told or shown the displayed formula for a hydrocarbon. The hydrocarbon has got double bonds, it's also got single bonds, so we've got pi bonds and sigma bonds. We're asked to count the number of sigma bonds and the number of pi bonds. So if we're counting sigma bonds first, if we use our blue highlighter, there's 1, 2, there's going to be a third one in there, 4th, 5th, 6th, 7, 8, 9, 10, 11, 12. We're going to get 12 sigma bonds, and we're going to have, in terms of pi bonds, we're going to have 2 there and there. Okay, so we've got 12 and 2, and the answer is, of course, D. And then in question 17, we're asked to consider which of these equations amounts to a propagation step. Okay, so we can rule out A immediately because A is the initiation step, so we can rule that out. So if we put a red mark against it. If we look at B, it is 2 radical species, so that would be a termination step. So again, rule it out. That leaves us with C and D, where we've got a radical species and a non-radical species. Now, the reaction here is between chlorine and 1-chloropropane. We're starting off with 1-chloropropane, and so we would expect to have a 1-chloropropyl radical being formed, which can go on to react with a chlorine species, or you can have a chlorine radical reacting with 1-chloropropane. Okay, so having formed your chlorine radical, we've got 1-chloropropane. So propane would normally be C3H8, so 1-chloropropane would be C3H7Cl. So looking at D, we highlight that. We've got 1-chloropropane, and of course it will react with a chlorine radical to give you the 1-chloropropyl radical, so we show that here, and HCl. Okay, so D is your answer. The reason C isn't the the answer is because you've got the formation of a hydrogen radical, which we don't get in this mechanism here. Okay, so if we put a blue tick next to the correct answer and write it down, that's got D. Okay, so that's 17 taken care of. We move on to 19. So the reaction sequence is shown below, and we're looking at two steps where HBr is added to an alkene in the first step, and then you've got what looks like a hydrolysis of a halogenoalkane in the second step. So in our question, it says the reaction, which type of mechanism, reaction mechanism is involved in each step. So we should have step 1 being an electrophilic addition, and step 2 would be the nucleophilic substitution using the OH. So we've got B as our answer. Okay, so if we put B in that box, very good. Okay, and then if we move on to just very quickly checking if there are any questions. There aren't, so you're happy with the answers I've got so far. So looking at question 26 and 26A part 1, you've got compound B being a member of this homologous series. It says name the homologous series and state its general formulas. Compound B looks like it is an alkene to me. It's got a double bond, carbon-carbon double bond. There are no other functional groups present. General formula would be CnH2n plus 1. Sorry, that's completely rubbish. CnH2n, I should say. So we're looking at an alkene here. Okay, so CnH2n. So the compound we've got there is an isomer of butene. So we've got propene, and methyl propene is the actual compound B. Okay. Part 2 says what reagents and conditions are needed to convert compound B into a saturated hydrocarbon. But in a saturated hydrocarbon, there are no double bonds, just single bonds. If we're going to have a hydrocarbon, we can't have any elements apart from hydrogen and carbon. So the only thing we can add across that double bond is hydrogen. Okay, so hydrogen would convert this into an alkane, a branch alkane. It would be methyl propane, and we would need hydrogen, so H2, and we would need a nickel catalyst. It's a catalytic hydrogenation. Okay, so catalytic hydrogenation would be our catalytic, I think I can spell that, hydrogenation. Okay. Very good. And then I believe there's one more question to do before we sign off. There we go. So C, the structure of compound F is shown below. So compound F is a diol of some description. In part 2, a student plans a 2-stage synthesis for preparing compound F and compound B. The synthesis first prepares compound E as shown in the flow chart. Draw the structure of compound E in the box and state the reagents for each stage on the dotted line. So we've been going from B to F, and we need to go via E. Okay, so F is a diol, we've got B, and so what we would need to do is react it with bromine, I'd imagine. So bromine, and what we would end up with is the dibromo compounds, Br here, H, and we would have a CH3 here, and we would have a Br, and we've got another CH3 here. Okay, so once you form that dibromo compound, you should then be able to, using a nucleophilic substitution mechanism and using aqueous sodium hydroxide, be able to achieve compound or make compound F. Right, so that brings us to the end of today's session. So it's been quite a whirlwind tour of the bonding and the reactions of alkanes and alkenes. If you do think of any questions that you weren't able to ask during the session, do please drop us a line, do email us, and we will be more than happy to get back to you. It's been a pleasure as usual. Take care, and I will see you again, hopefully over the course of next week and certainly next Sunday. Thank you very much for joining me. It's been a pleasure.